Hi, I'm Kevin. Today I'm gonna be talking about a competitive programming problem, firefighting. Now, let's see the problem statement, which is simplified so that we can be more efficient to get the problem. So, the hardness of this problem is hard gold or easy platinum. And here's the problem statement. In a tree, each edge has a weight. Define the weight of a path as the sum of weights of edges in the path. And you want to find the path P whose weight does not exceed C, such that the maximum distance between any node and path P is minimized. Note that the distance between the node and the path is minimum distance between the node and any node in the path. Here's our first tip, which is the path must be on the diameter. So why is that true? Suppose the black nodes and edges are our tree, and the path that we choose is the red path, and the blue line is the intersection between the chosen path and the diameter. Now, if we change that path, that red path, into the blue path, which is the intersection of the red path and the diameter, the minimum of the maximum distance won't change. Here's a simple proof of that. So what's changed is that the nodes in the subtree of U and the nodes in the subtree of V, for those nodes, their distance to the path increases, right? However, since they are not on the diameter and the diameter is x to y, we can claim that the distance between node U and any node in the subtree of U is less than or equal to the distance between node U and x. Similarly, the distance between node V and any node in the subtree of V is less than or equal to the distance between node V and Y. Why is that true? That's because suppose we have a node in the subtree of U, and the distance between that node and U is greater than the distance between U and X, then that node can be X instead, and the weight of the diameter will increase. That's lead to the contradiction, right? So because of these two properties, even if we cut off the edges in the subtree of U and the subtree of V, the maximum of the distance won't increase because the distance between the nodes in the subtree of U and V to the path is less than or equal to the distance between X to the U and the V to the Y respectively. So they are not the upper bound. So they are not the bottleneck. If you increase those distance, the maximum of distance won't increase. The second step is to binary search the maximum. So let the answer be the minimum of maximum distance. We can binary search the answer. To check if ans equals to x works, we want to check if there exists path P such that distance between any node and path P doesn't exceed x. So we can use another binary search to search for the most right position on the diameter that can be the left endpoint of path P, and the most left position on the diameter that can be right endpoint of path P, which means that if we move the left endpoint of path P to the right, then the answer will increase. Likely, if we move the right endpoint of path P to the left, the answer will also only increase. So we can use binary search to find what the most right position that the left endpoint can be moved to, and the most left position that the right endpoint can be moved to. In this way, after we move the left endpoint to the most right position and the right endpoint to the most left position, we can make the weight of the path P minimized. So the last step is to check if that minimized weight doesn't exceed C. And if it doesn't exceed C, then it works. So that answer equals to X works. Otherwise, it doesn't work. And here's all. This is all. So if you have any questions, feel free to contact me. Thank you.